We saw in the last video how we could determine if an argument was valid or not by creating a truth table. But it turns out a number of argument forms have already been proved as valid, and these are often known as rules of inference. So let's take a look. So this is the one we saw last time, where if Socrates is human, then Socrates is mortal. Socrates is human, therefore Socrates is mortal. So this turns out to be called modus ponens, which is Latin for method of affirming. And it seems, I think, fairly straightforward, right? We state that if something is true, then something else is true. We identify the first part as true, so we can conclude that the last part is true. So this is a valid argument form. Let's take a look at another one. Another famous one is called modus tollens. This is modus tollens, which is Latin for method of denying. Now this one looks similar, but not quite the same. Here we have P implies Q, or if P is Q, then Q is true. And we state that Q is not true, so we conclude that P is not true. An example of this could be if Susan, or pick a name, Susan eats her dinner, then Susan gets dessert. This is the mom and me talking. Susan does not get dessert. What can we conclude? Well, we can conclude that Susan did not eat her dinner. Right. So this, she does not get dessert, that's this negation of Q, and she did not eat her dinner is the negation of P. This is a valid argument. You can do the truth table yourself if you want. I'm not going to do it here. It is a very famous argument. Just like modus ponens is very famous, modus tollens is very famous. Modus tollens works because this is effectively the taking the contrapositive. Let's see. Effectively taking the contrapositive of the modus ponens. Right? Because if we have an argument, P implies Q, the contrapositive is not Q implies not P. And that's sort of what's going on here. We have that P implies Q, and then we're told that Q is not true. Well, it follows that P is not true either. Okay, so this is very similar to the contrapositive. And we know that the contrapositive is equivalent to the original statement. So we know that these two statement forms, are equivalent. It turns out there's a whole bunch of these rules of inference. So a rule of inference is an argument form that's valid, and we've already seen modus ponens and modus tollens, which are the two most famous rules of inference, but it turns out there's a whole bunch. And I'm not going to get into what all of these are at the moment. We're going to look at them on the next slide. So this is from the textbook, and I'm not going to go into great detail in this, but we've already seen modus ponens, and we've seen modus tollens now. Remember, the text uses a squiggly sign instead of a sideways L. Generalization is saying, well, if P is true, then I can conclude that P or Q is true, because I already know that P is true. Similarly, if Q is true, then P or Q is true. Specialization is an example. Let's do an example of generalization. An example of generalization would be, I ate an apple, therefore I ate either an apple or a pear. Right? It doesn't really get us anything directly, but it can be useful in more complex argument structures. Similarly, if I told you that I ate an apple and a pear, you could conclude that I ate an apple. This is specialization. Instead of becoming more general, we're becoming more specialized. Conjunction, if I know that P and Q are both true, those are my two premises, I can conclude that their and is true. Elimination, if I know that P or Q is true, and I also know that Q isn't true, I can conclude that P must be true. Transitivity. Transitivity is one we'll be seeing later on in the course. Here's an example. If we know that if P is true, then Q is true, and if Q is true, then R is true, then if P is true, then R is true. Let's see, a good example of this one. If X is greater than Y, and Y is greater than Z, then X is greater than Z. Not quite right because I'm not using the implications, but this is another example of transitivity. Proof by division into cases. That one, if you know that P or Q is true and that both P and Q imply R, then we can conclude that R is true. And the contradiction rule, if the negation of P implies a contradiction, right, that's not a variable, that's the contradiction, then we know that P is true. This is actually what we've been using with the knights and knaves puzzles. This is how a proof by contradiction works, is if we can show that one direction causes a contradiction, then the alternative is the only way that works. Okay, so I'm going to post a handout of this as well so you can see it a little bit more closely. Let's take a look. Let's take a look at this one, this argument. First, we want to write its argument form, right? So let's do the argument form. I'm going to call Helen doesn't care about her grade. I'm going to call that P. We can name them other things other than P and Q, but nothing springs to mind. Helen doesn't come to class. I'm going to call that Q. Here we've got Helen doesn't come to class, which is a Q. Therefore, Helen doesn't care about her grade, P. So let's write this out. P implies Q. Q, therefore P. It seems reasonable. The argument makes some sense. If Helen doesn't care about her class, about her grade, then she doesn't come to class. She doesn't come to class, so she must not care about her grade. Let's do a truth table. So P, Q, P implies Q, and then I'm going to just write these other ones, Q and P, out here. I do that just because I like to keep the premises together and the conclusion together. Okay. So P implies Q. True, false, true, true. Q is true, false, true, false. And P is true, true, false, false. And again, you don't have to do these two columns, double them up. Let's find critical rows. Here's a critical row. And here's a critical row. Make a note of that. But if we look at the conclusions, this one works. This one does not. Okay, so it turns out this is an invalid argument. So this is invalid. It kind of seems like it should work. Helen doesn't care about her grade, so she doesn't come to class. She doesn't come to class, so therefore she doesn't care about her grade. But what if something else caused it? What if she got really sick, and that's why she didn't come to class? What if her car broke down, and that's why she didn't come to class? What if there was an emergency in her family, and that's why she didn't come to class? There are many reasons that she might not have come to class. If she doesn't care about her grade is one of them. Right? But it's not all of them. So this is true. Right? If she doesn't care about her grade, then she won't bother to come to class. And if this one's true, that she doesn't come to class, well, we can't know for sure why she didn't come to class. We can't say that's because she didn't care about her grade. It could have been about something else. So that's why this is an invalid argument. In fact, this is commonly known as the converse error. So this is a converse error. And the reason is it sort of has the same reasoning as the converse. If you recall, if P implies Q is our implication, then Q implies P is the converse. Right? And we saw in the last module that the implication and the converse were not equivalent. So similarly, this argument uses the same idea as the converse, and it turns out that this is invalid. It will sometimes be valid, right? That's what this true conclusion means. It sometimes will work, but it can't be guaranteed to always work. So this is not a valid logical form. This is an invalid argument. Let's do another one. If I eat an apple a day, here, let's call this one A, I will never need to see the doctor. I will never need to see a doctor. I'm going to call this D. I sometimes have to see a doctor. Well, actually, let's change this. We've got this negation in here, right? Never need to see a doctor. And I could write this as not D, and this is D, and this is not A. But it's a little, I find it's easier to make the first row be all positives. So let's call it something else. Let's use N for never, need. And sometimes I have to see the doctor, which means not never. So my argument form is A implies N, not N, therefore not A. And we could have written it the other way. This is the same as A implies not doctor, doctor, therefore not A. Right? These are just binary. As long as this one and this one are different, this is going to be the same form. But for simplicity, I'm going to stick with this one over here. Okay, so this is my argument form. Let's do a truth table. We have A. Ooh, it's hard to read. We have A. We have N. True, false, false. We have A implies N. We're going to have not N. And we're going to have not A. So A implies N. Should be getting pretty good at that by now. Not N is false. Right, just the opposite. And not A is going to be the opposite of A. Now, remember, I'm not looking at those. Those are just to set my truth table up. Here are my premises. This is my conclusion. Let's find some critical rows. Looks like this is the only critical row, and it has a true conclusion. So that means this is a valid argument. In fact, if you look at it again, you'll recognize that this is just modus tollens. Right? Which we already knew was a valid argument. If you had drawn it the other way, the A implies D, not D, D, therefore not A, you would have also gotten the same truth table. But it wouldn't look as similar as modus tollens. This is the pattern that we get used to for modus tollens. Okay. Let's do another one. If x is greater than 2, then x squared is greater than 4. X is not greater than 2. Therefore, x squared is not greater than 4. Well, let's see. If x is greater than 2, so say x is 5, then x squared is 25, which is greater than 4. X is not less than 2, so say x is 1, then x squared, which would be 1, is not greater than 4. So, at the first glance, it all seems to work. Let's figure out its argument form. So I'm going to call this P, call this Q. So this one is not P, and this one is not Q. Let's write out a truth table. First of all, let's finish it. This is P implies Q, not P, therefore not Q. So this is a new argument form. This is not one we've seen before yet. PQ, P implies Q, not P, therefore not Q. If you try to rush these truth tables and do them in less space, what I've found is it makes it a lot easier to make mistakes. So not P, not Q. Okay, then let's look at this again. These are our premises. Conclusion. We don't care about those. Let's look for a critical row. Looks like we have two critical rows down here at the bottom. And one has a true value and the other does not. So, this is an invalid argument. Right, because we have that critical row with a false conclusion, but it kind of seems true, right? We said if x is, say, 5 and 5 is greater than 2, then x squared should be greater than 4. So, say 25 is greater than 4. If x is not greater than 2, then x squared shouldn't be greater than 4. Except, what about if x equals -5? So then what we have is -5 is not greater than 2. That is a true statement. But -5 squared equals 25, which is greater than 4, which breaks our conclusion. So this is an example where, again, sometimes it'll look true. It's going to look true for positive numbers greater than 2, or positive numbers less than 2, but it's not going to work if we use negative numbers. Okay, or some negative numbers. This is known as the inverse error. So this is called the inverse error. Because once again, we're sort of using the idea of the inverse. If P implies Q as our implication, then not P implies not Q is our inverse. And we know that these are not equivalent to one another. Okay, and as we can see from our truth table, the argument form does not work either. Okay, last one. If you go to GCC, then you have purple hair. You go to GCC, therefore you have purple hair. Well, let's write the argument form out. P implies Q, P, therefore Q. That's modus ponens. Which is valid. Right? We don't need to do a truth table to see that. Does that mean everybody in our class has purple hair? Well, no. And the reason is because even though this argument form is valid, so this is a valid argument form, it is unsound. And the reason is because this first premise is not true. Right? In order for an argument form to be sound, argument must be valid. Argument form must be valid. And all the premises must be true. Otherwise, it is an unsound argument. So this argument is unsound. Right? Pretty much, if the premises aren't true, we know nothing about the conclusion. This is sort of like a vacuous truth. Yes, the statement is true, but it doesn't mean we know anything about the latter part of the implication. It could be true, it could be false. Similar with soundness. So a sound argument is a valid argument, and the premises are true. All the premises are true. So that's why this argument, even though it is logically valid, it doesn't make any sense.